Okay, so now after introducing a lot of the details and ideas of nuclear reactions, let's now start to look at some of their consequences and, how do they actually happen in nature? The reason we're looking at all of this in astronomy is that, as I say here, we're producing enormous amounts of energy release. Look up at the sun. The reason we're seeing the light that we're seeing from the sun is nuclear fusion. Um, so yeah, so it's worthwhile to look particularly at the case of fusion, the power source of the stars. So what we're talking about here, as I just talked about before, are exergonic reactions, where the output state is in a lower energy state than the input state, right? And again, lower energy means deeper in the potential well, which means more stable nuclei in that resulting state, which means that we're moving from low to high in that binding energy per nucleon diagram, right? And again, the big example is taking 4 individual particles, 4 individual hydrogen nuclei, and eventually getting them into 1 helium-4 nucleus. And by looking at the binding energy curve, you can see that doing that once gives you 27 MeV of energy. You can always convert that to joules. And that energy is released as photons. So we'd like to know, can we actually produce a star that shines by doing this lots and lots of times in the core of the star? So the first thing to look at is sort of a plausibility argument for, and we can just use our own sun as an example. So the question we can ask is, how much hydrogen would need to fuse into helium in order to produce the energy released by the sun over its lifetime so far? Again, now we know a lot about what the sun is going to do in the future, but let's just say we don't know that, and all we know is the age of the sun, about 4 billion years. We know that the luminosity is equal to the energy, released per unit time. So we can sort of rearrange that and sort of integrate both sides over time in a way, and basically take the current measured luminosity of the sun, which is 4 times 10 to the 26 joules per second, or watts, and multiply it by that lifetime, right, which is 4 billion years, or if you convert it into seconds, it's something like 10 to the 17 seconds, to get the total amount of energy that's been released so far. That is eventually 10 to the 43 or so joules, which converts into 3 times 10 to the 56 MeV, mega electron volts. Again, it's just another unit of energy that you can convert from joules. But remember, the reason we're doing all this is to compare with this 27 MeV per reaction, right? One reaction involves 4 protons turning into 1 helium, and if it's roughly 27 or rounded up to 30 MeV per reaction, and we look at the total amount of energy that we need, we can divide those, and we realize that something like 10 to the 55 reactions are needed. This is just a dimensionless number that says, how many times do we have to do this in order to get this, right? Okay, now we have a number for how many times we would have had to convert 4 hydrogens into 1 helium. Now we can start to ask, is there enough stuff in the sun to do that, right? To account for all that. Now we can look at mass, right? One of these reactions involves 4 protons turning into a helium. So it involves converting 10 to the minus 26th kilograms of solar material. Processing that amount of mass is one reaction. Well, now we have a number of reactions, and now we have the mass per reaction, and we can multiply those. And when we do that, we get 10 to the 29 kilograms of hydrogen. That's what needs to have been converted from hydrogen to helium so far in its lifetime. Well, okay, now we can compare it to the actual known mass of the sun, which is something like 2 times 10 to the 30, which is about 20 times bigger than that. So that means that 1/20th of a solar mass had to have been converted from hydrogen to helium so far. That's a plausible number, right? If that number had turned out to be 1,000,000 times of the solar mass, then we know that it just can't work. But the fact that it's less and that it's just a bit less is plausible. We know that it's just the core of the sun that undergoes fusion and not the rest of the layers. So yeah, it makes sense. All right. Now, even though it makes sense, there's still another factor that we have to worry about, and that is the electrostatic repulsion between those protons. Right? If we try to shoot those protons together, a lot of them will want to repel one another because they're both positively charged. Yes, we know about the strong force that sticks things together, but you have to get really, really close together for this repulsive force to turn into an attractive force. This, as we go back to our thoughts about quantum mechanics, this is a potential barrier that you have to get past. Right? Remember when we looked at the quantum mechanical case, the energy of the beam of particles that was coming in was represented as this sort of constant line. Is it here? Is it here? Is it below the peak, or is it above the peak? And if it's above the peak, you can get past the barrier. There's more than enough energy to overcome the barrier. If it's below the peak, then that means that in the classical sense, the particle will just get reflected back, as I show here. So now we have to start to compare the average energy of the particles, the average kinetic energy of the particles. We have to compare it with the peak of this potential function, right? The maximum of the potential function. Is the average kinetic energy below it, or is it above it? If it's below it, that's bad news. If it's above it, then it's good news, because a good number of particles will get past the barrier into this attractive region, and fusion can happen. All right, so this is sort of part 2 of the plausibility argument. Remember, we're really talking about 2 positively charged particles approaching one another, so we can use the whole center of mass coordinates to turn it into an equivalent one-body problem. We've got our reduced mass, our relative position and velocity, and we can use the whole machinery that we built up before in the course to talk about these things. We are still talking about a gas or a plasma, so these are random thermal motions of the particles we're talking about. So we need to look at the average kinetic energy. The average, I could have written average of 1/2 mv squared in the brackets here. And when we talked about Maxwell-Boltzmann distributions, that average kinetic energy per particle turned out to be 3/2 kT. And now we'd like to know, is this average kinetic energy above or below the peak of that potential barrier? The peak of that potential barrier can be written on the right-hand side here by just using Coulomb's laws and how we went from forces to potential energies. Right? We have our Coulomb's constant. We have the Q1, Q2, right? The product of the 2 charges, which now we write using the Z notation for the atomic numbers of the nuclei, the numbers of protons multiplied by the charge per proton, divided by R, divided by the distance between them. And I'm using this Rn here because, again, what we're talking about is, can we get them close enough, right? This peak of the potential barrier happens when they're close enough to transition to this negative potential due to the strong force. So that distance tells us the peak of the potential. Okay, well, now we just have an equation that we can solve for the temperature. Right? What is the temperature needed to overcome the potential barrier? Higher temperature means higher kinetic energy, which means better chance of overcoming the barrier. And if we set these things equal, the temperature just has to be equal to that. And we can plug in numbers for just about all of those things. We still don't know exactly what to put in for R sub n, the size of the nucleus. We can go back to the basic experiments that showed us the size of the nucleus, right? Rutherford's scattering using alpha particles. That told us the size of the nucleus is something like 10 to the minus 15 meters, a femtometer. Well, if we plug that in, and use protons for the charges, we get a number. We get something like 10 to the 10 kelvins of temperature. If you remember from an earlier part of the course, lecture set 5, I think, when we talked about the conservation equations of fluid dynamics, we talked about the pressure gradient force. There was an example in the lecture notes that I think we skipped over in class, of what is the central temperature of the sun, just going by the balance between gravity and the pressure gradient force. We got a number of something like 10 to the 7 kelvins, about 10 to 15 million degrees. That's the number we get here is about a factor of 1,000 bigger than that. So this is kind of bad news. This says that the temperature has to be much, much bigger than we know it to be in the center of the sun in order to let fusion happen. But however, we know fusion is happening in the sun. So there's something wrong with this calculation that we just did here. It's telling us we're missing something. What we're missing is quantum mechanics. And the quantum mechanics tells us that we sometimes shouldn't just look at the actual size of something. Remember, when we're down in the quantum realm, we're down in the realm where the de Broglie wavelength, the actual sort of size of the fuzziness in the Heisenberg uncertainty principle, that size of fuzziness for small objects can be big. It can be bigger than the size of the object, right? It depends on the momentum of the object for the de Broglie wavelength. And if we're talking about something so small like a nucleus, if its de Broglie wavelength is bigger than the actual physical size of the nucleus, then we have no right to ever talk about that smaller size of a femtometer, because everything is fuzzed out, right? The uncertainty principle tells us that we're never going to be able to at this value of the momentum specified to give you a bigger de Broglie wavelength, we're never going to be able to specify anything down to that level of precision anymore. It doesn't make sense to talk about smaller sizes than the de Broglie wavelength. Remember, in the macroscopic world, the de Broglie wavelength is always much, much smaller than the size of the object. But in the quantum world, that's not always the case. All right, so let's try it. Let's actually say, well, let's say that all we need to worry about for this R sub n is the de Broglie wavelength, not the actual size of the nucleus. Let's replace R sub n with the wavelength. To do that, there's a little bit of a complication, right? If you remember, how do we write the de Broglie wavelength? It's Planck's constant divided by the momentum. Here we're sort of converting momentum into temperature, and if we want to then figure out what is the de Broglie wavelength, we convert this p into an h over lambda, and then we'll have to solve for the lambda in terms of the temperature for this whole thing over here. We get this over here. And it makes sense that the de Broglie wavelength depends on the temperature. A higher temperature gas is going to have a higher average momentum, and of course that'll be a different de Broglie wavelength. So it complicates the math a little bit, because here we were just solving for temperature in terms of things that we know. Now the thing that we're going to have to plug in there is a function of the temperature. But yeah, so let's just say and so the reason we're doing this, of course, as I said, if the wavelength, de Broglie wavelength, is bigger than the actual size of the nucleus, then the position of the nucleus is fuzzy or uncertain from Heisenberg's principle, and that's the number we should be using. All right. So we do it. We plug it in. We solve for the temperature again, and now we have this mathematical difficulty that we have a temperature equals some stuff with the temperature on the right-hand side. So we have to do a little bit more algebra, right? We have a T equals some stuff times square root of T. So what we do is multiply or divide both sides by square root of T, so that we get T to the 1/2 on the left equals just that stuff. And then we square both sides to solve for t. That's what we did over here. And if you notice that a lot of these things that were just to the 1 power, like k sub e and the z's, are now squared over here, just because we had to go through this algebra. We plug in the numbers, yay, we get the right answer. We get something like 10 to the 7 Kelvin, which is the realistic value for the core of the sun. And interesting, if we go back and use that temperature in the definition of the de Broglie wavelength, we find out that the de Broglie wavelength, which we're now using for this nuclear size, is in between, right? It's much bigger than 10 to the minus 15, the actual size of the nucleus, and it's much smaller than the size of atoms, of course. But it's orders of magnitude different from, say, the size of the nucleus. So when we're talking about these close interactions between nuclei, we've got to involve this idea of quantum tunneling, right? When the two particles get together by only one de Broglie wavelength, yes, it still might be big compared to what the strong force really cares about, but quantum uncertainty means that you can tunnel through that barrier even though you're further apart. That's sort of the plausibility for how fusion can work in stars like the sun. And we'll talk a bit more about how fast it actually happens next time.